Hello, I'm Ben, a developer relations engineer working on Navigation 3, and I'll be joined by Clara. In this session, we'll be covering everything you need to know about building adaptive layouts for your app with Navigation 3. After a brief refresher on the core concepts of the library, we'll cover what's new in the 1.1 release. That includes a deep dive on scene decorators, which can be used to add common UI elements such as top and bottom bars around your app's main content. To close things out, we'll take a look at how Navigation 3 is expanding to Wear OS and give you a preview of what we're working on for 1.2.
Hello, I'm Clara. First, let's go over some basic Navigation 3 concepts. Navigation 3 was built from the ground up with compose state as a fundamental building block. This means that it fully buys into the declarative programming model. You change the state you own, and we react to that new state. To start, the navigation backstack is just a regular list that you fully own. The backstack contains keys which can be of any type, and each key in the backstack maps to a nav entry that contains the composable content. As you add and remove keys on the backstack, navigation reacts by recomposing the content based on the current keys on the stack. To set this up, define your nav key and create a backstack with the key. In this example, the key extends the optional nav key interface. Then, invoke the nav display composable and pass in the backstack. Now, nav display also needs to know what content the key maps to, so you need to pass in an entry provider. The entry provider is responsible for providing a nav entry for a given key. In the nav display, call the entry provider DSL and add entries with the nav key and the associated content. And that's it. Nav display will first decide what to display, and then it calls your entry provider with the key to get the correct entry. In this example, the entry provider will return the home nav entry for the home key. By default, navigation will render the nav entry associated with the last key on the backstack. But what if you want a more complex layout? For example, what if you want to display multiple entries at the same time? This is where the scene interface comes in. A scene controls which entries are displayed and how they are displayed. This means that the same nav display can be used to show entries in different layouts, such as a dialog, a side-by-side list detail, a horizontal pager, a bottom sheet, or just a single pane. But how does the nav display pick the correct scene to show the entries? It does that by asking each of the scene strategy instances you pass to it. The nav display goes through a list of scene strategies in the order they were added to the list. And the first strategy that returns the scene dictates the entries to display and the layout to display them in. Nav display will then invoke the return scene to display the actual content. The list of strategies can be modified, and nav display will just recalculate and display the new scene. Now, how does the scene strategy decide whether to return a scene or not? One of the ways is by evaluating the entry's metadata. The nav entry has a metadata field, which is a map of string key to any values. Nav entries can opt in to be displayed by specific strategies through adding the metadata defined by a strategy. This gives entries control over how it wants to be displayed. In this example, the entry opts in to be displayed as a dialog. In our 1.1 release, we listened to your feedback and made several improvements to our APIs. In the past, scene strategies used to be passed in as a chain of strategies linked by a then infix. However, it was named as a singular scene strategy, and the then infix was not discoverable. So, in 1.1, we renamed the parameter to a plural scene strategies, and now it takes a list of strategies. But remember that order still matters here. As mentioned, the first strategy that returns a scene becomes the dictating strategy, and strategies are evaluated by the order they are added to the list. Next, in 1.1, we also improved the metadata APIs. As mentioned, the metadata is a map of string to any, which is not very type-safe. Also, the keys are commonly declared as string constants, so they are not readily discoverable. So, we improved them by adding a nav metadata key interface and a metadata DSL. Now, when you define a metadata key, the key can optionally implement the nav metadata key interface. You'll notice that the interface has a type parameter. The parameter represents the type of the data that is associated with the key. This means that when you define the key, you are also declaring the type of data it expects. This helps ensure you store the correct data type. With the nav metadata key, you can now use the metadata DSL. The DSL is a type-safe map builder that provides a put function, which accepts keys that extends the new key interface and the value associated with the key. The DSL returns a map of string to any containing the data you added with the put function. And you can use a plus operator to combine metadata maps. This allows you to declare modular, reusable metadatas, which you can mix and match to create the final metadata for a given entry. With the DSL, you can also write conditional logic to determine the final metadata that you want to add. Another new feature that was added in 1.1 is the support for shared nav entries. Nav Display now animates shared entries as shared elements when you use shared transition layouts. As mentioned, Nav3 can render multiple entries on the screen at the same time. And sometimes, the same entry can be shared between different screens. For example, consider a two-pane app with a screen displaying entry A and B. The app then navigates to a new screen with entry B and C. In this case, the two screens share entry B. Let's see what this looks like in an actual app. This app shows two products side by side on the screen. When you navigate to the next product, the product currently on the right moves to the left, and the new product is now displayed on the right. It works as expected. However, you'll notice that there is no transition animation when the entry moves from right to the left, and there is a flash on the right side. This is because an entry can be only displayed on the screen once. So the entry on the right side is dropped immediately when the screen is recomposed with that entry now on the left. In 1.1, we improved shared nav entries by animating them as shared elements. This allows the shared entry to exit the old screen and enter the new screen with a single continuous transition. Let's go back to the same app. Now you can see that as you navigate to the next screen, the product that is currently on the right side slides smoothly to the left. As mentioned, support for shared entries is added in 1.1, so all you have to do is apply shared transitions. Let's see what the code looks like. First, wrap nav display within a shared transition layout. Then, pass the provided shared transition scope to nav display. And that's it. Now, when the screen transitions from one to another, any shared nav entries between them will be animated as a shared element, resulting in a smooth transition. Now back to Ben to explain scene decorators.
Finally, 1.1 introduces scene decorators, which allow you to modify the scene calculated by your app's scene strategies. Scene decorators can be used to add UI elements such as top app bars and navigation bars or rails that you'd like to add at the scene rather than nav entry level. To illustrate this API, let's walk through the process of implementing a basic scene decorator that applies a border around the scene it decorates. To start, we'll define a border scene class that takes in a scene as well as some configuration for the border that it draws. Since border scene implements the scene interface, it needs to override the key, entries, previous entries, and content properties. Because border scene just wraps this input scene, it has the same entries and previous entries. For the purposes of this example, it can also copy the input scene's key, but more on that later. As for its content property, border scene uses a box with the modifiers necessary to create an outer border. And within that box, it calls the input scene's own content composable. Now that we have the border scene class, we need a way to use it. This is where the scene decorator strategy interface comes in. We'll create the border scene decorator strategy class as our implementation of the interface. This interface has just one method to override, decorate scene. Unlike the calculate scene method of the scene strategy interface, decorate scene can't return null. Instead, if the input scene shouldn't be decorated, you just return it as is. When determining whether or not to decorate a given scene, a scene decoration strategy can consider the metadata of its input scene, its nav entries, as well as any other state that it can access. The last step is to create instances of your scene decorator strategies and supply them to your app's nav display using the scene decorator strategies parameter. Now, when we run the app, we get a result like this. Just like we want, the borders are applied around all of the nav entry content, regardless of whether one or multiple entries are being displayed at a given time. Let's take a closer look at what's happening under the hood in these two configurations. When the window size is narrow, the two-pane scene strategy returns null during scene calculation, because there isn't enough space to display two panes side by side. Nav display then falls back to a single pane scene strategy which returns a single-pane scene. In the scene decoration phase, the blue border decoration strategy takes in that single-pane scene and returns a border scene that wraps it. The returned blue border scene is then passed as the input to the red border scene decoration strategy, which wraps it in another border scene. Now, let's look at what happens when the window size is wider. In this case, the two-pane scene strategy returns a two-pane scene, and the scene calculation phase ends there. The scene decoration phase follows the same flow as before, just with the initial input being a two-pane scene instead of a single-pane scene. An important thing to note from this example is that the class of the scene returned after scene decoration can remain the same, even when the class of the scene returned during scene calculation changes. This is noteworthy because NavDisplay animates transitions between scenes when a key derived from the class of the current scene and its key property changes. This can cause unexpected behavior when introducing scene decorators in an app where different scenes use the same key, such as in the Nav3 recipes list detail sample. In such a case, one solution is to provide an initial scene decorator strategy that copies everything from the calculated scene except for the key, instead using one derived from its class and key. This lets the following scene decorators just copy the key of their input scene. Following this approach, the list detail recipe now behaves like it did without any scene decorators. Now that we've covered the basics of scene decorators, let's see how they can be used for some more practical purposes. We've published recipes in the Nav3 recipes GitHub repo that demonstrate two use cases. The first shows how to create a scene decorator that adaptively switches between showing a bottom navigation bar or a navigation rail based on window size. And the second shows how to create a scene decorator that can display an entire scene in a dialog. We can't get into all of the details in this video. Here's a high-level overview of what those recipes demonstrate. In the responsive navigation recipe, we show how you can use Compose's movable content and shared element APIs to ensure that only one instance of a composable, in this case, the nav bar or rail, is composed at any given time. We also demonstrate how a scene decorator can consider states such as the current window size class when determining how to decorate a scene. In the dialog scene decorator recipe, we show one way that metadata can be used to determine if and how a scene should be decorated. And that's it for what's new in Navigation 3 1.1. Now, I'll hand it back to Clara to share updates on Wear OS and what's coming next for Navigation 3.
Support for Navigation 3 goes beyond mobile devices. Available today is a Nav3 integration for Wear OS with swipe dismissible scene strategy in Wear Compose Navigation 1.6 stable version. Simply add Remember Swipe Dismissible Scene strategy to your nav display, and the entries will be displayed in Wear material components. It also comes with full support for swipe gestures. Beyond the 1.1 release, we're also working on a couple new features for version 1.2. Yes, we heard you. We will be adding APIs to support deep links and APIs to pass events or state-based results between destinations. Currently, we have recipes to show sample implementations of both features, but we are graduating these recipes into APIs to make it easier for you. So, there's still more to come.
Thanks for joining us today. We hope you've enjoyed learning how Navigation 3 can make building adaptive UIs easier than ever. To view the recipes mentioned in this talk, as well as many others, check the link in the description. And last but not least, if you have any feedback or feature requests you'd like to share with us, please reach out through the GitHub or issue tracker.